Hello and welcome back to AP Physics. Where I want to start is kind of where we left off the other day. If we've got two vectors, we can add them by breaking them apart into their resultant vectors and then adding the x vectors together and the y vectors together and then making an overall x and y total vector. So here we've got water in the ocean is pushing a boat at 12 meters per second directly northeast, and a wind is blowing the boat 8 meters per second, 10 degrees south of east. What we want to do is figure out the actual boat speed, which would be a result of these two vectors, so adding them together. So we've got the current vector, which is 12 meters per second, which is 45 degrees. And then we've got the wind vector, which is 10 degrees south of east, which is 8 meters per second. So what we want to do is start by breaking apart these vectors into their components. So for the current, which is 45 degrees, we use sine to find the y component and x to find the, or cosine to find the x component. Then we break apart the wind vector into its x and y components. Here's the y using sine again, and x using cosine, which won't always be the case. I mean, every time x won't be cosine. It kind of depends on how the vector is defined. Then what we want to do is add up our y's. So we've got 7.5 and minus 1.4, because again, notice that 1.4 meters per second Vy is down, so it's negative. Putting the sign in your calculator won't tell you if it's negative or positive. You've got to look at it when you draw it. So, and then we add our x components together, and we get 16.4. Now that we have our x total and our y total, we want to make an overall vector with this to find the resultant. So we have to add them together. So we have our x total, which is 16.4 meters per second, and our y total, which is 7.1, which is positive, which means that it's up. And so we use Pythagorean's theorem to find the resultant magnitude, which is 17.8 meters per second. And then we find the angle using tangent or sine or cosine. We could use whatever ones, but considering we got these numbers first, we probably should use them. So we're going to use tangent. So 7.1 over 16.4 equals a tangent of theta. And we get 23 degrees north of east in this case. Let's see. So on to vector independence. So what's important here, the main takeaway is that we can look at the x components separately from the y components. We can look at the x separate from the y, and the x doesn't affect the y, and the y doesn't affect the x. They might be happening on the same object, but one does not necessarily affect, or one does not affect the other. So if we've got a boat that can move at 5 meters per second through still water, so right now we've got an overhead view of a river, and right now I've got the river turned off. That's me with the squeaky valve turning the water off. So how long will it take it to get across the river if the river is 30 meters wide? So if it's at 5 meters per second, that's 30 meters, so that should be 6 seconds. So 1, 2, 3, 4, 5, and 6 seconds to touch the other side. Now let's say I turn the water back on. Okay, and now let's say the water flows at 2 meters per second downstream, which in this case is going to be up or positive y direction. How long does the boat take to get across the river now if I turn the water on? And if the boat's still trying to propel itself at 5 meters per second east? Well, the answer is it's still going to take 5 seconds to get across the river. The only difference is it's going to float downstream some in the process. Okay, it's still going to take 6 seconds. So the boat was still moving at 5 meters per second in the x direction. The y velocity of the river does not affect the x velocity. Okay, so the fact that it's moving in the y direction does not affect its x velocity. It only affects its y velocity. So it was also moving at 2 meters per second in the north direction. Okay, but it was doing this at the same time. So it was moving at 5 meters per second east and 2 meters per second north. And the resultant is the boat that went diagonal. So changing the y does not affect the x. So I can change the y without affecting the x, and I can change the x without affecting the y. They're independent of one another. So, but let's say I wanted to know the total velocity of the boat. if it was moving at 5 meters per second east and 2 meters per second north, and I wanted to know the velocity relative to the shore, or the resultant velocity, what we would use is Pythagorean's theorem, 5 meters per second, putting the vectors tip to tail, 2 meters per second north, and we'd get 5.4 meters per second. So that's the overall speed. That's how fast it's moving compared to someone on the shore. Now, it went 30 meters across. How far did it end up downstream? Well, we said it took 6 seconds to get across the river, and every second that the boat was traveling, it also went 2 meters downstream. So 6 meters per second times 2 seconds, or flip those units, and you get that it would have floated 12 meters per second, or 12 meters downstream. And 6 seconds times 2 meters per second. What's the overall displacement? What's the resultant displacement? Well, we use Pythagorean's theorem again, and get 32 meters. So this is a side note that I would definitely take note of. The resultant vector does not have to be the longest vector. If I were to add these blue and green vectors, this A vector and this B vector, and if I were to add these vectors, and my resultant velocity would be shorter than either of the two. Why? Because they were partially canceling each other out. So the resultant is the sum, the tip to tail of the vectors. It's not necessarily the longest, so keep that in mind. Okay, so this is a good problem. We've got a boat, and the boat's in the ocean, and the ocean current is pushing the boat due northwest at 1.1 meters per second. Now the boat's engines can propel itself at 2.6 meters per second relative to the water. And the question is, how should the boat orient its engines in order to go directly east? So the current is pushing it northwest. Yep. And we want to figure out which way its engine, so that it would have a resultant velocity that is due east. I don't know how much it is. The only thing I know is the direction. So this is the ocean current vector in the 1.1, and we can orient the boat's velocity vector anywhere we want, but we want the resultant to end up going due east. Well, that should look something like this. So when I add the ocean vector and the engine vector, I should end up with something that's flat, that's pointed due east. So this is what I know about the situation. So and again, when I draw these, I don't have to worry too much about scale, because I'm using sine, cosine, tangent, and Pythagorean's theorem to do this. So and if I didn't already say, notice that the resultant vector isn't the longest vector in this case. I mentioned that a little bit before. So now we want to figure out the angle. So what is theta? What angle should the boat do that in order to end up with this resultant that's due east? Well, what I need to do is take my A vector, my ocean current vector, and break it up into its components. So using sine and cosine, I get 0.78 and negative 0.78. And what I know about this boat velocity vector is that it needs to cancel out with the y. So for this y going up, I need this same amount of y going down. So I know that this side of it is 0.78. Well, at this point, I've got a triangle, I've got a right triangle with two sides. So now I know everything I need to know about that triangle. I would use the sine of theta equals 0.78 over 2.6. Don't put the negative in your calculator. It's going to give you kind of wonky results. But I did make this negative because technically it is, because it's down. And so now I know theta equals 17 degrees, in this case south of east. And how fast would the boat be moving overall? What would its resultant vector be? Well, I know that this component right here, using trig, this is 2.5 meters per second, just using the right triangle, 2.5 meters per second. And what's left over of it, this vector is the 2.5 minus the 0.78. So adding the x vectors together, the ax and the bx, finding my overall x vector. My y vectors add up to 0. My x vectors add up to whatever that would be, 1.7 meters per second east. And that would be how you do that. So the red is the 2.5 minus the 0.78. We're skipping this, and I think we're